So, hello everybody. I am Suzanne Hernandez, Marketing Manager at Nanoe, and I introduce you Frederic Rousset R&D Engineer. I repeat it for the last person who joined us. Today we are going to focus on metal FDM troubleshooting. Last month we already had a webinar about ceramic FDM troubleshooting, and you can find the recording on our YouTube channel. So today we are going to focus on metal and in particular H13 FDM troubleshooting. I insist that we are going to focus on what is likely to going wrong when you will print and doing the post process. But most of the case, our technology is easy to use and nothing happened wrong. So let's begin. So first, I'm going to introduce you our company for the person who don't know us already. So Nanoe is an advanced material provider. We are specialized on ceramic powders and advanced ceramic powder for cutting-edge industries such as aerospace or medical application. We have 10 specialized engineers and one R&D center. We are producing industrial batches from 100 kilograms to 1 ton. And we are more than 10 years of experience. The company has been created in 2008. Since 3 years, we decided to created a new line of product, zetamix technology, that make accessible our powder to 3D printing and to 3D printing with the FDM technology. So why we are doing that? Because we noticed that in the ceramic and metal additive manufacturing market, the processes and the solution are not easy to use and to begin with. And we wanted to make accessible this technology to great companies, to smaller ones. So our vision is to make accessible the ceramic and metal 3D printing, as I said earlier. So our technology has a low investment. It's affordable to a lot of different companies, from laboratories to small and medium companies. It's important to us to have an easy-to-use solution. So our filaments are suitable with mostly every 3D printers, as long as they are with a direct drive system. The properties of materials is very important for us because we are a material provider. So it's important to us to keep good material properties, whether it be for metal or for ceramics. So our material can withstand extreme temperature, for example, or are good wear resistance. They are close to the properties of materials produced with other processes. When we think about 3D printing, we think about intricate design, such as hollow-out parts or internal channels. And our technology allows to print ceramic and metal parts with this kind of characteristics. As I said earlier, the properties of materials is important for us, and our final part made with ceramic and metal zetamix filament show a good density. For metal is 95%, and for ceramics is more than 99%. And last point, our technology is fast, is a fast metal additive manufacturing technology. That means that the preparation of the machines and the cleaning of the machine is not long and is really easy to use. So our offer, of course, our first offer is the material. We provide 3 different types of ceramics: alumina, white zirconia, and black zirconia, and 2 different types of metal: stainless steel, and A13 for hot and cold tooling applications. We also provide machines, printers, a debinding kit, and a sintering furnace. I insist that we are not a machines producer, we only resell them to be sure that our client has the right material to print and to produce their parts. I'm going to focus now on each process of metal. So first, H13 process. So it's an easy process with 3 steps. First, the file preparation and the printing, the same that with polymers, PLA or ABS. And the last step is the sintering under neutral gas. It's very important to make sure that your part has its final properties and its final densities of 95%. For the stainless steel, it's slightly different. The 2 first steps remain the same with the file preparation and the printing, but the sintering is under hydrogen, so you need special furnace, whereas with H13, the zetamix furnace is a good furnace to sinter the parts. So now we can focus on the troubleshooting. So here we really focus on what can go wrong in the technology, but as I said earlier, most of the time it's easy to use, and the printing or the debinding and sintering, nothing happens. Just for the beginners with our technology, the first time you print and you sinter the part, it can have some issues because it's the first time for you. And these webinars is a mean to make you save times and know what are the possible issues you can face. But when you print with our filaments after some weeks or sometimes, it's okay, you don't have any troubles anymore. So first, I'm going to insist about the content of this webinar. We are going to focus on our filaments, and we are not focused on other polymers or printing issue. If you have other issue like under extrusion or over extrusion, you can check Simplify 3D website, where you can find a very interesting troubleshooting guide. We are going to focus on things that can happen only with our filaments, and all the other issue, you can check the website like Simplify 3D. So first, the first issue when you print a filament is the filament can break mid-print. So our filaments are little more brittle than PLA or ABS filaments because they are highly loaded with metal powders, so they are a little more likely to break, in particular if they are under pressure or if the printer head is jerking. So Fred, what are your tips to solve this issue?
Oh, yes, hello everyone. So first of all, I'm just going to insist on the fact that I would recommend to use 3D printers that are direct drive, not Bowden ones, because it will reduce the stress that you have on the filament. So this is the first tip I would give you. I would highly recommend this one. Second of all, so we have a couple of solutions for the filament that are breaking mid-prints. The first one is to use a spool holder as well as a bearing of it. This will help to reduce the stress that you have on the filament. You can put the spool holder on top of your filament, as you can see on the photo, and it is working quite well. The second solution is I would highly recommend to avoid any retraction that you have on the filaments. On the guidelines that we are giving out, we don't put any retraction and we avoid it because you are going to do some back and forth inside the 3D printing head, and this isn't good for the filaments. And lastly, if you have a printer that is equipped with a filament run-out sensor, this is the best because if the filament is breaking during the printing, it will automatically stop and you can continue your print without any impact by resuming it, and it is quite easy. This is the best solution.
Thank you, Fred. So let's focus on the second issue. Oh, sorry. So the second issue is the grinding. Sorry, I'm too fast. So the grinding is when the filament is squeezed between the gears and thus break because the screw is too tight. So Fred, what is your advice about this trouble?
So for this problem, for the grinding, this is a problem that can be quite frequent for some filaments that are brittle, but we have some good solutions for this, for all filaments. I will insist on the fact that this filament in particular is quite sensitive. The H13 or the 316L are quite sensitive filaments, and you need to have a good hand to find the good tightening of the screw. If you screw it a bit too much, you're going to smash your filaments with the gears, and if you don't screw it enough, the filaments won't be dragged inside the printer. So it can be quite hard for the first prints to find the good spot, the sweet spots about screwing by the tightening of the screw that you have. But after a couple of prints, you shouldn't have any problem to find the spots. I will insist on it again, but you should avoid retraction. This is the same principle as above for the grinding. If you're doing some back and forth inside, the gears can grind the filaments, of course. And lastly, you have to clean your gears and avoid as much as possible any scraps that you have inside the gears. This will help that your filament won't be attacked by the gears, if possible.
Thank you. So third trouble is the clogged nozzle. So if your filament isn't broken or crushed and there is no molten filaments that come out of the nozzle, it means that your nozzle is clogged or is likely to be clogged. So Fred, what is the solution for this issue?
So for this issue, I will separate it in two parts. For the first one, if your nozzle is clogging at the start of your print, this means that your bed isn't adjusted well enough. For polymer filaments, this is quite easy to find the bed level, but for metallic filaments, it is quite sensitive, as well as the tightening of the screw. Filament is a bit more sensitive, so the bed level should require a bit more experience to do it, but it isn't quite hard. After a few pins, you should be able to find this problem. But yeah, if your nozzle is clogging at the start of your print, it should be the bed level that has a problem. If it is during the printing, you must clear your nozzle. This is the first thing to do. If it isn't working, you can change your nozzle as well as take a bigger nozzle that will reduce the pressure that you have inside your printer, so it won't clog as much. If you still have some problems, you can try to tweak a bit the different parameters that we have. The two ones that I would recommend should be to lower the printing speed or increasing the printing temperature. For the guidelines that we give out, I think the printing speed should be around 10 to 20 millimeters per second. If you have some problems with the nozzle, you can go down around 5 millimeters per second, I would say. This should help a lot. If it isn't, you can increase the printing temperature. For the H13, it is at 180 degrees to 200 degrees. You can go above like 210 if you need to, if you find it useful. I won't go over 215 because after that, I think the surface, the quality of the piece, the part you have printed isn't good enough. So don't go over too much.
Thank you, Fred. So another issue you can face is the interlayer adhesion. So sometimes the layer you are printing will not adhere with the previous one, and there is a lack of connection between those layers, like in the picture. So Fred, what are your tips with this trouble?
So yeah, for this trouble, you won't find this troubleshooting for polymer filaments or even ceramic filaments. It's quite rare. Even for this filament, we don't see that often. But if it happens, even if it's quite rare, the best solution that we found is to lower the printing speed. As I said, 500 meters per second should resolve the problem completely. If you still have some problem, increasing the printing temperature can be good as well. If you don't want to reduce the printing speed or touch the printing temperature, you can try to play a bit with the size of the nozzle and the width of the layer so that your layers will smash a bit more and it will adhere much better.
Thank you. So we are going to focus on extruder issues. So what are the solutions?
So yeah, I wanted to do a quick recap on that because you have, it isn't like polymer filaments or common filaments. Yeah, if you have a failed print, you must clean your extruder, the gears and the nozzle very cleanly to remove any pollution or any scraps that you may have before starting your print again. This is quite important. And if you have some recurring problems with this, if you have it daily or on the same day, even if you clean your extruder, try to clean every part of your printer. This is very useful. We do it at our company around 1 time per week, and we find it very useful. And lastly, I will try to insist a bit on the fact that if you have some unnecessary gaps between your parts of the printer, material can amass in it. So if you can try to have as less as possible as unnecessary gaps in your printer, this is the best. So try to clean your printer as much as possible. This will help a lot your prints.
Thank you. So now we are going to focus on debinding and sintering issues. So first, a little reminder about how to set up a furnace. So Fred, can you explain us how to properly set up a furnace and how to set up the gas?
Yes, so we wanted to do a quick recap on the diagram that we have for the furnace. This is a recommendation that we have for the sinter that we are selling, of course. So for the different recommendation that is working very well with us, you must put the crucible at the center of the furnace and put 2 thermal shields on each side of your furnace. If you can follow the diagram is very well done. The shield should be placed, the different shields, thermal shields that are on the diagram should be placed there. For the cylinder gas on the left, the pressure at the regulator should be at 0.2 bar and the rate flow around 0.6 liter per minute. For the pressure, I wouldn't touch it. 0.2 bar is enough, and if you go over it, you can or you may break your tube. So I won't touch it a lot. I highly recommend to stay at 0.2 bar. For the rate flow, we will see it later in the presentation, but 0.6 liter per minute is the recommendation that we have, but we will see that we can go a bit above depending on the piece you want to sinter. Hello? Is it me or is it Suzanne that has a problem? Can someone fill me up on the chat? I'm not quite sure. Ah, yeah, okay, it is Susan. Okay. Sorry. Thank you for the answer. I don't have the presentation. So I guess we have to wait that she comes back. I don't know if I can share my screen because I should have it too, but I will try to pick it up if I can. 1 second. I guess she will come back, but for now I'm going to try to take it off. I think this is good. Not quite sure. Yeah, okay, I have it. We're saved. Can someone confirm it if you can see my screen, if you have the presentation? I think it is okay. Okay. Okay, I think I'll continue a bit. Thank you for the answers. I'll continue, and Suzanne will catch off, I guess, if she can. I don't know if I have any news about it. Not for now. I'll continue a bit. So for the first, where I was at the diagram, I think. Yes. So after the diagram, I will show a couple of troubles that we have during the debinding and the sintering. I will focus on the fact that debinding is only thermal debinding inside the furnace. We don't have any chemical debindings. The first one is the fact that the first trouble can be that the parts are melted. As you can see on the parts, on the image, the part is completely metal. It is quite rare. We never have this. This is the, oh, hello back, Susan.
Sorry, I don't know what happened. My connection is, I don't know. I'm back.
Yes, I put the presentation myself because I had it. So,
thank you.
I'll keep it here. So yeah, I was just talking about the metal parts that we have. So this part is quite rare. We had this only one time. The solution is quite simple. You have to decrease the sintering temperature. We have a guideline for this. You should be at 1350 degrees for the sintering of your part. You shouldn't go over it. If you go over it, you can have some melted parts. Not as much as you see on the picture, of course, but it can happen, and try to follow the guidelines if you can.
Thank you. So I'm coming back with a trouble explanation. So another trouble you can face are the blisters. In the picture, you can see little blisters and big one. So that means that the binder is getting out of your part properly. So Fred, can you explain us how to solve this issue?
Yes, of course. So the blisters are quite common on most printers, or even in injection molding. It is happening quite a lot. We have a very good solution for this that is working very well. So if you have a lot of parts inside the furnace, the problem is you have a lot of binder that you have to get out. So try to not overload the furnace, and try to not have parts that are that have a lot of weight, because you have a lot of binder to get out, and this is quite hard. This is what makes a lot of blisters on your parts. If you have to do some parts that are quite heavy, you can increase the gas flow rate. So as I said before in the diagram, I recommend 0.6 liter per minute for the flow rate. But you can go higher if you need, because some parts are quite heavy. And if you have a bit higher, it will help get out the binder much more easily. So for this part, it was a part, we didn't show the photo, but believe us, this part had a lot of blisters on it. It had like 7 or 8 blisters on the surface, and we had to do something about it. The part was done at 0.6 liter per minute at first for the gas flow rate. So we put it at 1 liter per minute, and yeah, you can see that the part is now perfect. We don't have any blisters on it. So the solution worked quite well. And this is the same for this one. So this one, we didn't even try to do it at 0.6. We knew that the part is quite big and heavy. It was a very heavy part. So we put it around 1.2 liter per minute at first, and the parts gotten out of the furnace very well. So the solution is working very well for now.
Thank you. So another trouble is oxide appearance. So when you remove your part from the furnace, your parts are partially oxidized or totally oxidized on the surface. So Fred, what are your tips on how to solve this issue?
So for this is quite obvious. If you have parts on the surface that are oxidized, this means that you have some leaks somewhere. You should check the leaks if you have some on your furnace, or tighten the flanges. If you still have some problems and you have some parts that are oxidized like this, you should check for the ceramic tube. This means that the ceramic tube can broke, so you must replace it.
So another trouble is a twisted part. So like in the picture, your parts are twisted in one way or the other, and is often coming if the ratio width height is too high. So we are a lot of solution. One solution for this. So Fred, can you explain?
So yes, for this part, I'm going to insist on the fact that often when this happens is that the ratio of the width and height are quite different, and this is why it twisted a bit or a lot depending on the piece. But sometimes it isn't the ratio width height. It can happen. It is very rare, but if it is happening, we have a perfect solution that is working every time, and this is to print the layers alternating clockwise and counterclockwise. So not every slicer is doing it. I know that Idea Maker is doing it. They implemented it a couple of patches ago. So Idea Maker is doing it. So this is perfect for us. I'm not quite sure if any, I think other slicers should do it, but I'm not quite sure which ones.
Thank you. Now we are going to focus on deformations. So this trouble is when parts are distorted in some areas, like the first picture is an extreme example, it's a big fail, and the other you can see just a little deformations, but no, the part didn't fit the dimension anymore, and it can be a big trouble. So what are your solutions?
So for this trouble, for the deformation, we have a couple of different deformations. So the first one was the twisted parts. For this one, we can help this one by printing some supports or some wedges of the same material. So as you can see on the bottom right photo, we printed some supports or some wedges to on the bottom and on the sides of the piece, which helped the piece not to deform. So this is the solution that is working quite well that we are using recently. We used it on the top photo as well, but we didn't kept the wedges that we used. And that's all.
Thank you. Another kind of deformation is when the deformation is only on the bottom, like in the picture. So what does it mean, and what is happening, and how to avoid this?
So for this problem, we recently discovered this problem because it is quite rare that that is the case. But if your parts are quite crushed on the bottom, as we can see on the photo, you can try to center it differently. This means that you can try to turn your parts upside down and try to think if it will help. If it is not helping, because you try to redistribute the weight of your parts inside it. So if it is not helping to bring it upside down inside the furnace, try to redistribute your weight. This means that for the infill, for example, you can try to put 85% infill on the bottom parts that you have, and on the top parts, we'll try to put like 20% of the infill. This means that the top part will be much less heavier than the bottom one. So this shouldn't crush the part. So this part, we are going to resinter it next week. We haven't had the time to do it, but we are going to try it with the infill that we have said.
And follow us in LinkedIn to see what is the final part and how it is.
Of course, we will keep you updated if we can. For this part, you can see it, but this part was a bit crushed on the bottom, not as much as the one before, but this one was a bit crushed. So we changed the infill. We put 20% on the top one and 80%, I think, on the bottom one, and the part was perfect. It wasn't crushed, so it worked very well.
So thank you. So we are done with sintering and debinding issues. If you want more documentation, you can visit our website. In the filament pages, you can find design guide and guidelines to help you to print and to post-process your parts. We also have a YouTube tutorial channels when you can watch a tutorial about debinding, sintering, or printing. This month, we are going to focus on sintering and how to set up the gas. And you can also find on our YouTube channels the recording of our webinars. For example, last one about ceramic troubleshooting, if you want. So now we are going to focus on answer and questions. So I saw before my interruption that there was one question in the discussion area. So feel free to ask your question, and Fred and me will be our best to answer you. So if I remember, the first question. So if I remember, the last question was about if we can change. I'm not sure if we can change the filaments to make sure that the grain of metal is not too big and will not clog the nozzle.
If we can change the filaments?
Not the filaments. Yes, the grain, the metal loaded, to make sure that the grain, the powder, is not too big and will not clog the.
Oh, yes. Can the clogged nozzle issue be resolved by amending the powder mix using powder metal of appropriate size and quantity? Yes, it can help lots. For the size, for the powder that we are using, we use this solution. If you have a different powder, it won't have the same problem. Of course, if you take your appropriate size and historical morphology, this should help a lot. I'm not quite sure. I don't have the specifications on the powder that we have here, I know that they should be around 10 to 20 micrometers. And our circle, I don't have a lot of information on this, but yes, you are right. That using the appropriate size, the appropriate powder should help for the clog of the nozzle.
Yeah, but I'm insist in the fact that to make sure to have a big density, like 95% of final part, we have no choice to load our filament with a lot of metal powder, and it's more likely to clog the nozzle. So it's a choice whether have a dense part and a clogged nozzle, or a less lower density and printing more easy. And it's also a choice of us. Second question, do you have any idea how to avoid cracks? It's appear during sintering of copper parts.
Copper parts, we don't do any copper for us, but if you have any cracks, I don't have the info. I'm guessing that you're doing some chemical debinding. If you have some cracks while you're doing some sintering, this means that your thermal debinding, your thermal cycle shouldn't get adapted enough. Maybe your ramp is a bit too quick, or you are not doing like a 2-hour holding time at the sintering temperature. I think this is the thermal cycle that isn't appropriate for the material that you're using. If you are using some debinding, chemical debinding, I think you should keep it a bit more in the bath, or try to wait that the part is cooling enough before removing it from the bath. If you're removing your parts from the bath when it is hot, it can crack. So wait a bit of time, and you shouldn't have any problem. But if it is for copper, I'm not quite sure. We are not doing the copper material here, so but the problems should be the same.
Thank you. What density do you achieve, and how do you measure it?
So the density that we achieve, we are over 95% for our metallic filaments. We measure it with different calculations. The most obvious one is the Archimedes. I hope I'm saying it right. The Archimedes solution, and we are doing it as well geometrically. So we have a couple of different calculations, and we try to find the best one, the most suitable one, and that's it.
Thank you. Another question about the molten parts during the sintering. Could incomplete debinding also be the root cause and not a too high sintering temperature? How to adjust debinding? Interesting question.
Yes, this is a quite interesting question. If your parts are molten, this should come from the formulation, I think. This means that the formulation isn't adapted enough, or the cycle of your debinding isn't adapted, because you are doing a ramp quite harsh, and it can't melt apart. But with the filaments that we are using, it is quite impossible that you have a melted part after debinding for metallic filaments. It is always we never had a part that was melted after debinding. It was always for the sintering. So this can happen depending on the formulation, but for the filaments that we are selling, this shouldn't happen.
Thank you. So other question, do you, I'm sorry, too much question.
Yeah, there are all, thank you for your questions. There are a lot of questions.
And there are too quick. So what are the dimensional tolerance we achieve on final parts?
So what do you mean by tolerances? I guess we have something on the design guide for alumina and zirconia. I don't have the numbers in check. I should guess it's 0.1 of tolerance. I don't have we have those tolerances for the ceramic filaments that we have. For the H13, this is in progress. We should keep you updated because the design guide will come out soon enough. And that's all. I don't have a quick answer for this, unfortunately.
So a question about debinding. Do you use the same binder system for all your different powder? I think you mean filament, and how you can answer it.
Yes. So for this question, very good question. Of course, we are not using the same binders for every system. Each powder is different. Each powder will react differently with each binder. So we try to use some binders that we know that are working, and we try to replicate it on our filaments. But sometimes this isn't the case. So I think we have maybe 4 to 5 filaments for now that are good, and maybe 2 of them have similar binders. But the powder is very powder dependent, so you can't use as much the same binder like for metallic and ceramic filaments. So this is why it takes sometimes to develop new filaments.
Thank you. Other question about the shrinkage. Is the shrinkage the same between X and Z? And sorry, I don't know how to pronounce it in English.
I don't see the question.
It's a question of Tobias Tenzel. In the answer and question.
Oh, yes. What percentage do you achieve? And no, thank you. Same shrinkage in X. No. So for the metallic filaments, we have a guideline on this. I think we communicate on this. The X and Y, we have the same shrinkage. It should be around 18%, I think, for the X and Y. And in Z, I think it's a bit less. I think it's like 17, but we can check on the guidelines. X and Y should be the same. Z, depending on the filament, it can change a bit. Sometimes it's the same as X and Y.
Thank you. A question about the printing. I think the connection was not stable. In the slide where you speak about the brittleness of the filament, you speak about the race 3D and you say the race 3D are equipped with. Oh,
yes, sorry. I hope, sorry if I speak a bit too fast sometimes, or maybe the accents. It's a filament sensor that will detect if your filament is breaking or not. If the filament is breaking, the sensor will detect it, and it will stop your print. And you just have to come back, see that your print is stopped because the filament is broken at the top or even inside the printer. You just have to reload it, and you can resume your print without any problem. So some printers have some, most of them, I think, have some detector sensor for the breaking of the filament. So I would recommend to have one because it is very helpful for some filament that can be a bit brittle.
Thank you. A question about debinding. Do you check the weight loss during debinding on are the guidelines for minimum value of weight loss?
Who asked this question?
In the discussion.
Oh, yeah.
I don't see the
check
name
the
of
weight
the person.
loss during debinding or other guidelines for minimum value of weight loss. Yes, the guidelines are for the minimum value of weight loss, of course. So I'm not quite sure if you're talking about the ceramic ones that we are debinding chemically, or if you're speaking about the metallic ones. I will answer both, so you have the answer for both. For the chemical debindings or the ceramic ones, we weight the parts each time after debinding to check if the weight loss is sufficient. I won't say any value because I don't have it in mind for ceramics. I'm mostly on metallic. but we check the value to see if it is enough. And for the metallic filaments, we check it after the sintering. We don't check it during the process, because we are doing the debinding and the sintering in the same furnace, in the same cycle, without interruption. So we are just checking at the end if we have the good weight loss that we are aiming at, and each time this is good. So we don't have any problem here.
Thank you. To complete the Fred answer about ceramic debinding, so after the chemical debinding, your part had to lost at least 5% of its mass. So you need to check the weight, and it's 5% of its mass. So after its comments, so you can a lot of comments about the deformation of parts.
Microstructures. I will try to answer the question of Manoj Jain, who is asking, have we done any microstructure analysis on the final metal parts? We haven't done it a lot. We have some. It is currently in the process. I know we have done some checks, but I don't have the results now. But we are checking regularly how it is. But I don't have the info on me right now. You can email us, and I'm sure we can answer it with the appropriate person, if possible.
So I think we answer all the questions. So we are waiting just 2 more minutes if there are more questions.
Thank you for your questions. They were quite interesting. I hope we answer them as much as possible. If you have any other questions that will that you have in mind later in the day or in the week, you can email us, and I'm sure we can answer it after that.
And I insist that we have a YouTube channel with a lot of explanation, for example, about mass loss for ceramics. You can find the information there. And this month, the video is about how to set up a furnace. The next month is about how to sinter a ceramic part. And in December, the video will be about metal gas, and we will have similar content than with the furnace diagram of this presentation. It can be a little reminder.
I saw that Scott answered quite well to one of the questions, so thank you. This is exactly it. And this is why for the thermal debinding, of course, you can stop the process at the debinding step and check if you have the weight loss. But as he said, the part is quite fragile, and it can be a risk to cut the process in half. So thank you, Scott, for answering as well.
So I think we answered all the questions. Thank you for attending the webinar. So you are likely to be contacted by one of our cell engineers this week. And I think we will share this webinar recording on our YouTube channel if I succeed with the lack of connection I had. And sorry again for that. And thank you for attending.
Thank you, Suzanne. And thank you, everyone, for coming by. Have a good day.
Goodbye. Have a good day.